Hello, everyone. This is Tianwei Zhang. I'm currently an assistant professor from Nanyang Technological University in Singapore. And I'm very happy and honored to present our talk titled Analysis and Mitigation of Function Interaction Risks in Robot Apps. This is a joint work with Dr. Yuan Xu and Professor Yungang Bao from Institute of Computing Technology, Chinese Academy of Science in China. Today, we are in the golden age of robots, and our life is full of different types of robots, ranging from the vacuum, drones, manipulators, to humanoids. And these different types of robots has been widely applied to different scenarios, like the smart factory, the intelligent farms, and automatic logistics. And it has been expected that by the year of 2023, the robotics market will reach the $241.4 billion US. The robots are becoming more smart. It is expected to perform more intelligent tasks. Meanwhile, we also require the robotic apps running on these devices to become more intelligent. And then these apps are becoming increasingly complex. Okay. So generally, these apps is composed of different functions, and these functions are required to handle the data received from environment. This includes voice interaction, image recognition, and path planning. Okay. So when the apps are become more complex, which means that the function interactions will become more frequent. Okay. These functions interact with each other to achieve end-to-end tasks. And meanwhile, the high interaction between different functions also increase the difficulty for the robot app development. Okay. A promising solution to simplify the development of the robot apps is crowdsourcing. Okay. So we have the robot operating system platform, or the ROS platform, which provides the open source repositories and which contains different types of function packages. And then a developer is able to download these functions from the ROS repository and customize their own functions. And then the developer can integrate the downloaded functions with their own customer functions to finally form the desired app. Okay. So this app will be finally deployed on the robot. Okay. And user is able to use smartphones to interact with the robot and launch missions. So the robot is able to start the task with and interact with the environment. Okay. When the task is finished, the robot will send the feedback to the users through the smartphone. Okay. So this is the entire life cycles for the development and also the operations of the robot apps. Okay. In this talk, we consider a threat model, which the repository may contain the malicious package, function package. Okay. The reality is that the ROS repository is open for everyone to upload the functions, to share the function packages with the developers in the robotics community. However, the ROS does not provide any security inspections over the uploaded package. This gives the adversary an opportunity to upload the malicious function packages. Okay. And then if the developer downloads its functions from the ROS repository and integrate it to his own apps, okay, the app will become malicious, will become compromised. When the compromised app is deployed on the robots and runs in the environment, this can cause very severe consequences to the robots as well as the environment. Okay, this is a threat model we consider. Okay. So in order to fully understand the possible consequences caused by the malicious package, we need to understand the interactions in the robot apps. Okay. We use a navigation application as an example to show the interactions. Okay. So the navigation app is responsible for accepting the data from the environment, the sensor data, like the cameras, like LiDARs, and then process the data and then make the decisions to move the robot from one spot to another spot. Okay, so it has 3 stages. The first stage is perception. Okay, this stage is used to receive the sensory data from different sensors and then process the data, like to figure out the surrounding environment. Okay, after this perception phase, the app is able to figure out is to output some interpretation about the environment, which will be forwarded to the next stage, which is the planning module. The planning module is responsible for making the long-term actions based on the output of the perception module, perception stage. Okay, and it needs to either make the exploration plans or the path planning plans. Okay, and after the action is figured out, it will be sent to the next stage, which is the control module. Okay, so the control module is used to enforce these actions and ask the actuators of the robots to do the corresponding actions. Okay, so we can see that through the entire process of the navigation, so different nodes in different stages are highly interactive with each other. Okay, so generally the interaction can be categorized in 2 types. Okay, the first one is called the direct interaction. Okay, the direct interaction means that the nodes is directly connected logically. Okay, so in this workflow, we can see that some nodes are directly connected, which means that one node will send information flow to another node. This is direct interaction, and they have the direct dependency between these 2 nodes. Okay. The second category of interaction is called the indirect interaction, which is denoted as dashed arrows in this figure. Okay. So the indirect interaction, the nodes involved do not have direct connections. Instead, they will use the environment as an intermediate state to affect with each other. Okay. So for instance, some nodes inside the control node are not connected to the nodes in the perception module directly. Okay. However, the control node is able to affect in the environment, and then the environment will further affect the functions of the module, the nodes in the perception module. So this is the indirect interaction through the environment. Okay. So after figuring out the 2 types of the interactions, we present our first contribution of this project, which is about the function interaction risk analysis. So specifically, we review the interactions in different robot apps and propose 3 different types of the interaction risks that could potentially affect the security and the safety of the robot apps. So the first type is called the general risk, and this is caused in the direct interaction, happens in the direct interaction. Okay, so the key idea of the general risk is that multiple nodes will share the same state. Okay, so as shown in the left figure of this slide, we have multiple yellow nodes. Okay, so they share the same state of the robot, which is the black node. Okay, and they share these nodes using one topic, which is green rectangular, and this is a single topic general risk. Okay. And alternatively, it is also possible that these yellow nodes share the same state through multiple topics. This is a multi-topic general risk. Okay, so in either topology, it is possible that one of the yellow node is malicious, controlled by the adversary. And in this case, the adversary can try to send the malicious messages or flag the dummy state of the robots. And then the state of the robot will be compromised, which will affect other yellow nodes. Okay. So this is a first type of the risk, general risk, caused by the direct interaction. The second risk we consider is called the robot-specific risk, okay, which occurs in the indirect interaction. Okay, we call it robot-specific risk because it is caused by one of the robot specific features, the mobility. Okay. So two nodes are involved in this robot-specific risk. The two yellow nodes in this figure. Okay. The first one is the image-related node, and the second one is the max velocity-related node. Okay. So generally, the image-related node is used to process the images captured by the cameras of the robots, and then make the perception decisions, like if there are any object around, if there are any traffic light, what is a traffic light around? Okay, so this is the responsibility of the image-related node. The max velocity related node is used to make decisions about the maximum velocity of the robot. And this is key to adjust the velocity of the robots. Okay. So these two nodes must coordinate each other in order to make sure that both of them can function correctly. Okay. So, however, if one node is malicious, and then the entire operation of the robot can be totally compromised. Okay. So for instance, if the adversary controls the max velocity related node, and he can intentionally increase the velocity of the robots, so the robots will move at a much faster speed. So the cameras on the robot does not have enough time to capture the surrounding environment. And then the image-related node is not able to fully recognize the objects around, surrounding objects. And in this case, the image-related node will make the wrong decisions. It may miss some objects because the camera does not have time to capture it. Okay, so this is the indirect interaction because the max velocity related node affect the environment and then affect image-related node. The third category of the risk is called the mission-specific risk. This is also happening in the indirect interaction risk. Okay. And we also have two nodes involved in this mission-specific risk. Okay. Event-related node and action-related node, the two yellow circles in this figure. Okay. So we call it a mission-specific risk because this is not general. It is specifically for different types of missions. Okay. As shown in the table in the slide, we consider different types of scenarios, including the domestic, warehouse, city, and specialized. Okay. So for each scenario, the robot is expected to perform following some descriptions, following some rules. Okay. So if either the event-related node or the action-related node is compromised, and give some wrong information. And then the robot will make wrong behaviors, which will violate the missions, the description of the missions. Okay. So specifically, the event-related node denotes nodes in the perception module, which is to percept and interpret the event. And the action nodes are the nodes in the control module, which are used to make decisions about the actions of robots. Okay, so they are not directly connected, but the action-related nodes will affect environment and then affect event-related node. So this will be an indirect interaction. Okay, so if an adversary controls action-related node, it may make the robots take the wrong actions, which can affect the state and state of the robots and also environment, which can further affect event-related node. So this will be an indirect mission-specific risk, interaction risk. Okay. All right, so these are the basic descriptions of the three discovered interaction risks. Okay, so given these risks, our second contribution is to introduce a new methodology which is able to mitigate these risks. So the key idea of our mitigation solution is to introduce a set of coordination node. Okay. This coordination node is used to check the information flow of different across different nodes and inspect if there are any risks. If so, the coordination node will be guided by some policies specified by the users or the developers to regulate this. Okay. So the coordination nodes are generally inserted between two potential risky nodes. Okay. So we also provide some different types of the policies for different types of risks. Okay. This table gives a general description about these policies. And we also give more detailed explanation in the next following slides. Okay, so let's see how the coordination node can be used to regulate, to mitigate different types of risks. Okay, so first is a general risk coordination node. Okay, so specifically for this type of the general risk, if it is a single topic, okay, in order to insert coordination node, we first can convert it to the multi-topic. Okay, this is pretty simple. We can just add more topics for each node. Okay, and after that, we can insert a coordination node between the topics to the final state of the robot. Okay, so after that, each message from each yellow node must go through the coordination node before passing it to the state node. Okay. In this way, the coordination node, which is a yellow, which is a purple circle in the figure, is able to inspect each messages. Okay. We provide different types of policies for the regulation of the general risks. So this includes like blocking. We just block the actions if it is malicious, and we can also select actions based on different types of the orders or the priorities with or without time limit. Okay, so more details can be found in our paper. For the second risk, which is robot-specific risk, okay, so we inserted two coordination nodes. The first one is after the max velocity relative nodes, okay, and the second one is after the image relative nodes. And these two nodes are also directly connected to coordinate the information. Okay, so basically these two nodes will inspect messages from the max velocity relative node and the image relative node to make sure that they are not affected. They will not affect the robot device. Okay, so we also provide a set of the rules for the risk regulation, like to block, to adjust the velocity. Third, for the mission-specific risk coordination risks, we introduce a coordination node right after action relative node to inspect the actions from this node. Okay, and if this action is malicious, this node has a policy which can directly block the velocity control actions to make sure that it will not compromise the safety of this robot. Okay, all right. So these are the different ways to insert the coordination nodes. So next, let me introduce our third contribution in this paper, which is design and implementation of a new system called Itron. Okay, so the Itron is designed to include these mitigation solutions to protect the safety and the security of the robot apps. Okay, it is divided into two components. The first one is the app instrumenter, which is done in the offline. Okay, so basically, given a robot app, okay, so this module is able to discover all the potential risks inside, and then it is able to insert the coordination nodes into this app. And after that, we have the instrumented robot app, which has all the required coordination nodes inside. Okay, so the second module is called the security service. Okay. After the instrumented robot app is deployed on the robots, the security service will keep monitoring the runtime of these apps, and it will monitor this every workflow, every information flow across different nodes, and check if there are any real-time risk happens. And if so, the risk controller will follow the policies specified the users to regulate these potential risks and to make sure that the the robot's state will not be compromised by these risks. Okay, so through the whole pipeline, our Itron system is able to guard the security of the robot systems, robot apps. Okay, even some nodes are malicious. Okay, so we perform comprehensive evaluations to demonstrate the effectiveness of our method and system. Okay, so specifically, we select 110 single function apps from the ROS open source showcase website, which cover 24 different robots. Okay, and we also include 4 multifunction apps, and this includes the home-based, auto-race-based, and also we include the AutoWare and the Baidu Apollo, which are the 2 production applications for the autonomous driving systems. So first, let's see the performance, the risk identification. Okay, so for the 110 single function apps, we are able to identify all the possible risks in this, which can severely threaten the safety and the security of the possible robots. And for the 4 multifunction apps, we are also able to identify a total of 198 risk interactions for different apps and different categories. Okay. And next, let's check the effectiveness of the risk mitigation. Okay. So after we identify these risks, we use Itrons to insert the coordination nodes into the applications to get the instrumented robot app. Okay, so different applications may have different numbers of the coordination nodes. This depends on the complexity of the app and also the identified the risks. Okay, so and also we provide different types of the policies for each coordination node and the topics. Okay, so we have more details about the guideline for the policy selection in our paper. Okay, so this policy selection will be determined by the user's specific scenario. Okay, and finally, we measure our performance overhead. Okay, so for the offline overhead, this is mainly caused by the detecting the risks and also inserting the coordination nodes. Okay, so this table shows the result. We can see that for the simple applications, the processing time of the offline overhead is just like within 1 second, which can be ignored. Okay, even for the complex applications like the home-based auto-race, Apollo and AutoWare, the entire offline process can be done within 5 seconds. So the conclusion is that the processing time is determined by the number of the topics and nodes in the application. But generally, this time is pretty short, and it can be done in a very quick time, in a quick manner. Okay. Next, more importantly, we consider runtime overhead. Okay, so we insert different numbers of the coordination nodes and check its impact on the latency. And we can see that even we have like 10 coordination nodes, the latency is within 5 seconds, milliseconds. This can be totally ignored and will not affect the operation of the robot systems. Okay, and we also deploy we also demonstrate an attack and deploy our solutions in a physical world. Okay, so we package our malicious code and upload them to the public cloud sourcing platform. And then we download these packages to launch our attacks on a real robot device, which is Turtle 3. Okay, so without our coordination nodes, the Turtle 3 will be compromised and it will easily hit the walls or the doors. Okay, so after we enable our Itron system with correct policies, the robot can run safely without hitting any obstacles. This also shows the practicality. This also shows demonstrates the effectiveness of our solution. Okay, so to conclude, we gave the first study about function interactions for the common robot apps for the security and the safety, and we introduced a new system to detect and mitigate the risks by the malicious interactions. And also we conduct experiments to evaluate the effectiveness of our solution. And we are very happy to answer any questions you have. Thank you for listening.